Okay, we're going to go ahead and finish up the very last bit of section 8.1b, and that is talking about the conditions for constructing a confidence interval. And this is really important, and we've actually already highlighted a lot of this in chapter 7. And so our three conditions are random. So what we need to do is we need to make sure that we have a simple random sample from our population, or that if we're doing an experiment, our people who are our volunteers are randomly assigned a treatment. And so if we don't make that, then everything that we're doing is for naught, because then we have no implication on what does this tell us about the population, or is there a cause and effect. So remember, with our experiment, we're looking for cause and effect, and with randomly selecting from a population, then we are looking at taking our results and explaining it to the entire population. So we have to make sure we do this, or else what we're doing is just silly, because it's not going to tell us anything about what's true. Okay, the second one is the normal condition. And so we need this because for our probability. And so our sampling distribution needs to be approximately normal. So if we're talking about proportions, we have to do the n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. Exact same thing that we had in chapter 7. Now the normal condition for means, either the population is normal, or our sample population is large. So we have to have greater than 30 or more in our sample to make sure that we meet that normal condition. And the last one is independence. So either we're sampling with replacement, or if we sample without replacement, we have to meet that 10% condition. Sampling more than 10% will give us more precise results, but again, we have to use a very special formula, which is really complicated, and really you'd want a computer to use that, so we're not going to do that. Now, our method of calculation does assume a simple random sample, not a stratified sample or a cluster sample, because then you'd have to have some more complex formulas. So what we're doing is just for a simple random sample. And that's okay, because if you decide that later on you really want to get into probability and statistics and being actuarial or going to insurance stuff, and you want to do a lot of this type of stuff in research, if you're going to be a doctor, then you'll look at how those formulas are, and you'll learn how to work with the computer programs that'll actually calculate that for you. Now keep in mind that our margin of error is only accurate if the survey or experiment is done well. Undercoverage and non-response can lead to additional errors. So just be careful about that. Okay, and so now we're into section 8.2a, and what we're going to look at is estimating a population proportion. And so now we're doing confidence intervals for a population proportion. And inference about a population proportion usually rises when we study categorical variables. So again, categorical variables here with our proportions. So 95% in this category, 5% in that category. So just a review from chapter 7, the shape, we have that normal condition where it's going to be normal if we meet that n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. The center of our sampling distribution should be the same as the center of our population distribution. And then our spread is going to be that square root of p hat minus p hat all over n square rooted. But we can only use that if we meet that 10% condition. Since we typically don't know our original p, with our large samples, p hat will be close to p, so that allows us to go ahead and substitute in p hat now for the p in our standard deviation formula. So sample problem that you'll see, Mrs. Smith's class took a simple random sample of 102 pennies and wants to construct a confidence interval for the proportion of pennies more than 10 years old in their collection. So let's kind of give background here. Miss Smith has this huge jar of pennies, and there's more than 2,000 pennies in that jar, easily. So what they did is they took a simple random sample of 102 pennies from the jar, And they're going to count how many in there are actually older than 10 years. Their sample ends up having 52 pennies more than 10 years old in the collection and 45 pennies whose date was less than 10 years old. Check the conditions for constructing a confidence interval for p hat are met. So first thing, is it random? Yes. We took a simple random sample of 102 pennies. So we're good to go. Is it normal? So we have to check, normal is n times p greater than or equal to 10. So the nice thing here is we don't have to do n times p is greater than or equal to 10 because they tell you exactly how many. So is 57 greater than or equal to 10? And then is 45 greater than or equal to 10? So that's the same thing as doing n times p, but a little bit less work, recognizing what you want and what you don't want if those numbers are both greater than or equal to 10. So yes, it's approximately normal. And the last thing is it independent? Well, we probably didn't take a penny, put it back, take a penny, put it back, and go from there. So is it reasonable to assume, actually we don't have to assume because we know, there are more than 1,020 pennies in the jar. So we are good for using our standard deviation formula later on when we start calculating. And so that's what we're going to do each time. Because if we don't meet our conditions, we can't calculate our confidence interval with the tools that we have right now. So if you don't check, then you can do all that calculation for nothing and you look silly. Okay, constructing the confidence interval for P. So we talked on the last video about how we do our point statistic. So this is going to be our p hat, plus or minus our margin of error. And margin of error consists of two things, a critical value and the standard deviation of our statistic. So really, we're doing that point estimate plus or minus z star is the critical value because it comes from our normal curve, and or we can get it from our z table. And then our standard deviation is also known as our standard error because it's telling us that variability on both sides to help us get a margin of error. So standard deviation, we will use p hat instead of p in the standard deviation formula. So here's our standard deviation formula. The standard deviation of p hat is square root of p hat minus 1 times 1 minus p hat all over n. And again, this is known as our standard error. So our standard deviation is our standard error in this confidence interval. And then we have the critical value c, now z. Now what's really important about that critical value c is it comes from that normal curve. And so if I want a confidence interval level of 95%, then when I'm looking at my normal curve, for my sampling distribution, I'm assuming this is what I want to kind of estimate. And then if I want a 95% confidence interval, I want 95% of the values in there to give me a good confidence interval. And so for that, I need to figure out what is this z value? What is that z score? And what's interesting is because if this is a standard normal curve, this is 0, standard deviation is 1. This on this side is negative z. And so as long as you can calculate one of those values, z or negative z, you will have that critical value z for our confidence interval. And then what I do is I times that by the standard deviation. So it takes my value here in standard deviations and multiplies it by how big are those standard deviations actually. And that's how we get that margin of error. So looking at our sample problem, Use table A to find the critical value Z for each confidence level listed below. So again, here's our curve. We want 95% in here, which means to find Z, I need to know this, or I need to know this. And so if I'm looking at my table, I need to know area under here, or I need to know area under here. And so I've got two options. The easiest option is finding the pink area. So what is the pink area? Well, I'm going to take my 100% and I'm going to subtract the 95%, which gives me 5%, which is 0.05 as a proportion. And then because that's actually being divided up, that 5% between these two pink spots, and I only want to know this pink spot on this side, I take that 0.05 and I divide by 2. And that's what gives me the 0.025. So I'm going to flip over to the next page because I actually have my table there. So this comes from our formula sheet. And when I want to find the critical value for a 95% confidence interval, I'm going to take the leftover percent, 5%, divide by 2, 0.025, and I'm going to find 0.025 in my table. And so you use that to figure out my z-score. So I'm going to look on the inside of the table and find something that's close to 0.025. So 0.025 is somewhere in between here, 0.025. No, I need to go bigger, 0.025. Ooh, here we go, 0.025. Perfect. I actually have the value. So then the z-score for that is negative 1.96. But because our z-score and how that works with our thing, that could be this z or this negative z. So when we're talking about this critical value, it doesn't matter the sign we get, we just turn it positive. Because as we work it out mathematically, it really doesn't matter if it's positive or negative, it will give us the same answer in the end. So now, if I want to find for 80%, I'm going to take the leftover percentage, 0.20 as a proportion, and I'm going to divide by 2. So now I'm going to find the 0.10, and that'll give me my critical z-score. So 0.10, ooh, we're really close. We're somewhere in here. And it looks like this one's a little bit closer. So when I look over, I get negative 1.28, and it's closer to the 8 than it is the 9, so negative 1.284 maybe. And that gives us just kind of an estimate to work for our critical z-value. And remember, we always change them positive just because in the long run it makes it easier. You don't have to deal with double negatives and all that sort of stuff. Okay, so the table is fine and dandy. Out of 3 years of teaching, I've only met 2 students who prefer a table to a calculator. And so what we're going to do now is talk about, well, how do I do that in the calculator? And we use the inverse norm in the distribution menu. And so the inverse norm tells me, okay, inversely in the norm, I'm going to start in the middle, I'm going to work my way out, what's that z-score going to be? And so we do an inverse norm with that area, the same area number we'd be looking at before, where I take half the leftover percentage, with a mean of 0 and a standard deviation of 1. And we use that because in that table, that is a standard normal table. And so we want to figure out that standard normal table value. So we need to use a mean of 0 and a standard deviation of 1. And so when we do that on the calculator, we get a more exact value. Because remember, the table just kind of rounds it. So 0.02501. And this gives me a negative, but remember I changed it to positive, 1.959963986. And you are free to round this. I would feel comfortable rounding this to 1.96. They're going to look at answers in both forms because the 1.96 is what you would get from the table. That's what they're going to probably look at the most often. But if you use a more exact form, they'll have that answer there for you also. So they'll be able to double check and see if it's right no matter which way you do it. Okay, so the next problem, what if I had a 99% confidence interval? Well, what percentage is left? 1%, which looks like 0.01. And then I divide that by 2 because I've got my two tails, and I get 0.005, which means to find my critical z-value, I'll inverse norm. My area would be 0.005. My mean is 0, and my standard deviation is 1. And that'll help me find that critical z-value. Which is 2.5758, so on and so forth. Okay, so now we're going to put all this stuff kind of together, get an idea of how this works. We are going to look at a one sample z-interval for a population proportion. So we're working with proportions. We're doing a z-interval because it's a normal curve, so we do z-intervals. And it's a one sample because I'm only taking one sample from the population and evaluating just that one sample. So here's our formula for the confidence interval. We're going to take our p hat, we're going to add and subtract, that's how we get the number above and below that p hat, the z star, so our critical value, times that standard error, standard deviation of the sample. So again, this only works when we meet the normal condition and when we have an independent and a random sample. So Miss class took an SRS of 102 pennies. We already checked the normal condition. We already checked independence. We already checked the random condition and discovered that 57 were more than 10 years old. So right now I'm going to go calculate 57 divided by 102. Which I may not want to actually use, 0.5588, so on and so forth. Calculate and interpret a 99% confidence interval for P, the true proportion of pennies from the collection that are more than 10 years old. Okay, so I'm going to start with P hat, which is 0.5588. I'm going to plus or minus, and now we're going to do a 99% confidence interval. So I need to figure out my critical z-value for 99%. Luckily, we did that up here. 2.5758. And we're going to times by the square root, and we're going to do that standard deviation. So 0.5588, and then 1 minus 0.5588, 0.4412. all over our sample size, 102. So I'm going to go ahead and start with that standard deviation. 0.5588 times a 0.44, divide by 102. Then I'm going to square root it. So I got a standard deviation of 0.049. Then I'm going to times it by that critical value, 5758, which means that this is going to be 0.5588 plus or minus 0.1266. So now I'm going to take the 0.5588 and I'm going to subtract 0.1266, which gives me a value of 0.4322. And then I'm going to go back and I'm going to do 0.5588 plus 0.1266, which gives me 0.6854. So this is our interpretation right here. We are 99% confident, because we did a 99% confidence interval, that the interval from 0.4322 to 0.6854 captures the true proportion of pennies that are more than 10 years old. So this is going back to our problem and looking at, hey, what's going on here? So now the question is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? So now they're asking you to look back at that confidence interval and ask, is 0.6 in my confidence interval? And since it is inside this interval of 43% to 68%, then yes, it's plausible. Yes, 60% is in our interval. And there's our problem. Okay, our next one, and our last one for today. Alcohol abuse has been described by college presidents as the #1 problem on campus. It is an important cause in death in young college adults. But how common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined frequent binge drinking as having 5 or more drinks in a row 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. So what's the population and what are we trying to measure? So our population is looking at U.S. college students. That's who we're gathering information on. And what we're trying to measure is the proportion that frequent binge drink. And why is it important that they defined that? Because to some people, binge drinking may be getting drunk once a week. Some people it may be 3 times a week. Sometimes 3 times in 2 weeks. And so by putting a definition on that, it gives them kind of a leg to stand on. These people met these requirements, and that's why we decided that they were frequent binge drinkers. And so it doesn't have to be a common definition to everyone out there, but when they define it that way, it says based on our data, these are the people who met that definition. So it's really important that when you're doing a study, you line out information like that. You can't be really vague about it. Check the conditions. So our first condition is it a random sample? And so yes, it is, because we had a simple random sample, because we had this many randomly selected of 10,904 students. Why do I put that down? So anytime I need to figure out what n is or our sample size, I have it right there in my conditions. Okay, the next part is, let's see, random and then normal. So how many people were binge drinkers? Well, let's see, 2,486. Well, that's greater than or equal to 10. How many are not binge drinkers? So 10,904 minus 2,486. So 8,418 is greater than or equal to 10. So we're good on the normal front, we're good on the random front. And then we're going to move into independent. So we probably didn't select with replacement. So is it reasonable to assume that there's more than 109,040 college students in the United States? Easily. There's colleges alone have more than that. Okay, so now that we've checked that, that means that we're allowed to do our calculations. So the next thing we're going to do is we're going to go ahead and calculate the critical value for a 99% confidence interval. So our Z star is going to be equal to the inverse norm with an area of half of whatever is left over. So if I have 1% left over, I want half of that 1%. which is 0.005, a mean of 0, and a standard deviation of 1. So inverse norm. So my critical z-value is 2.5758. And we're good there. So now find the interval. So now I have to figure out, well, what is my p hat? So p hat is really the 2,486 students out of the total 10,904 that are considered binge drinkers. So 2,486 divided by 10,904. And we get 0.2279. So I'm going to leave it as 0.228 because that is really close. So I'm okay with rounding it. So that's my proportion of my sample. I'm going to add and subtract my critical z-value, 0.5758. And then I'm going to times by the standard deviation. So 0.228. And then 1 minus 0.228. 0.772. All over my sample size, 10,904. And that's going to allow me to calculate that confidence interval. So now I'm going to go ahead and do 0.772 times 0.228. Then divide that by 10,904. And then square root that answer. So I got 0.004. And I'm going to times that by 2.5758. So now I have 0.228 plus or minus 0.01035. And so now I'm going to go ahead and create that interval. So the lowest value is when I subtract, so 0.228 minus 0.01035. Uh-oh, I made a mistake somewhere. Oh, 01035, there we go. Accidentally had an extra decimal in there. So 0.21765. And then I'm going to take the 0.228 and now I'm going to add the 0.01035. Got another weird decimal in there. There we go. Which gives me a 0.23835, which is a really small interval compared to our last problem. So now if we're going to interpret this in context, we are 99% confident that the interval from 0.21765 to 0.23835 captures the true proportion of U.S. college students that are frequent binge drinkers. And so what you're finding here is that this step here, identifying our population and what we're trying to measure, helps with this interpretation because we're seeing all that right here. True proportion, U.S. college students that are frequent binge drinkers. Okay? Our conditions that allows us to make these calculations and then that interpretation. This is really like our 4-step free response problem, except for they gave you little prompts for each part. If you did all of this without the prompts, that is a full free response that you could turn in on any test. And I will expect you to do that.